Imagine you are building a precision robotic arm or designing an aircraft's control surfaces. How quickly does the system respond to your commands? This speed is absolutely critical for performance, safety, and efficiency in countless engineering applications. In engineering, particularly in control systems and electronics, rise time, often denoted as TR, is a crucial metric that quantifies how quickly a system's output changes from a specified low value to a specified high value in response to an input. The main factors influencing TR are the system's bandwidth, its natural frequency, and its damping ratio, all fundamentally determined by the system's poles and zeros. The underlying reason these factors are so influential lies in the dynamic behavior of the system. Think of a system's poles and zeros as its fundamental genetic code. A system's dominant pole, the one closest to the imaginary axis in the complex plane, largely dictates the speed of its transient response. The further the dominant pole is from the origin, the faster the system tends to respond. Closely related is the system's bandwidth, which represents the range of frequencies it can effectively process. A higher bandwidth means the system can respond more rapidly to changes, directly translating to a shorter rise time. Furthermore, the natural frequency of a system describes how fast it would oscillate without any damping. A higher natural frequency generally leads to a faster response. However, this is tightly coupled with the damping ratio, which indicates how quickly those oscillations decay. An underdamped system, with a damping ratio between 0 and 1, will have some overshoot but can achieve a faster rise time than an overdamped system, which is slower but stable without oscillation. Critically, a higher-order system, one with more poles, can exhibit more complex responses and may not always follow simple direct relationships, making careful analysis essential. Understanding these influences allows engineers to design and tune systems for optimal performance. For instance, when designing a control loop for a motor, engineers will select components and controller gains to place the system's poles in desired locations. This ensures the motor reaches its target speed quickly without excessive overshoot or instability. In analog circuit design, engineers might adjust component values like resistors and capacitors to expand bandwidth, thereby reducing signal rise times for high-speed data transmission. The goal is often a balance between a fast rise time and acceptable levels of overshoot, which is the amount the output exceeds the final steady-state value before settling. A fascinating insight is the inherent trade-off between rise time and overshoot. Generally, to achieve a very fast rise time, engineers might design for a slightly underdamped system, accepting a small amount of overshoot. Conversely, eliminating overshoot entirely usually requires a higher damping ratio, which in turn slows down the rise time. This critical interplay is a cornerstone of control system design, known as the speed versus stability trade-off. It highlights the art of engineering in finding the sweet spot for a given application's requirements. Mastering the relationship between bandwidth, natural frequency, damping ratio, and system poles is fundamental for any engineer aiming to precisely control system dynamics. By understanding these factors, you gain the power to not only predict how a system will behave but also to actively sculpt its response characteristics, ensuring robust, efficient, and timely operation in everything from robotics to communication networks.